All right, good morning, everyone. I was worried my camera wasn't working for a second. Yes, good morning. It's actually well over midnight for me, but good morning to everyone else present here. The innate drive to find the truth has kept the human spirit of ingenuity alive for as long as civilization. Our curiosity has progressed very far from looking at the stars and wondering what the universe is made of. But very few achievements can be compared to when we made the colossal discovery of the Higgs boson. We are now celebrating the 10th anniversary of this remarkable feat of scientific progress. I am Uday Bhanu Singh, a student of astrophysics at the Georgia Institute of Technology and an alumnus of Shiv Nadar School, Noida. Along with my co-hosts, Praneel and Suhana from Shiv Nadar School, I invite you to partake in the exploration of the significance and history of the God particle. Before we move on, I would like to welcome our dignified guests to today's event. We have with us Ms. Anju Soni, who is the principal of Shiv Nadar School, Noida, Ms. Monica Sagar, who's the principal of Shiv Nadar School, Gurgaon, and Ms. Anju Wal, who is the principal of Shiv Nadar School, Faridabad. We also have the president of Shiv Nadar School, Mr. Avnish, Ms. Shashi Banerjee, who's the director of education at Shiv Nadar School, and also Mr. Matthew, who is the head of connected learning at Shiv Nadar School, Noida. We are honored to have with us Dr. Archana Sharma as our main panelist today. She has had a tremendous career in physics that spans over 3 decades, and her contributions to the scientific community continue to flow in. She currently works as a senior advisor for relations with international organizations at CERN and has previously been involved in numerous experiments at the organization. She has fine firsthand experience in the field that we've wished to explore today, so saying that it's a privilege to have her would be a severe understatement. In addition to her contributions to research, Dr. Sharma founded the nonprofit Life Lab Education Research Foundation in New Delhi in an effort to amplify the reach of science amongst younger minds. Since 2016, the organization has given rise to numerous initiatives that focus on nurturing the spirit of science in school students, and we are glad to be working with them again today. Ms. Vinita Sharad, who is the lead program coordinator of STEAM and Science at Shiv Nadar School, has been working with Life Lab Foundation for quite a while now, and we have collaborated in the past as well to provide early exposure to latest discoveries in the field of pure science, and we are happy to bring another event to all of you today. I am thrilled to be talking to all of you about this feat of modern science. The importance of this achievement supersedes boundaries like no other scientific revelation. As we will discover in our conversation with Dr. Sharma, the Higgs boson comments on the scientific nature of the fundamental idea of mass and what the universe is really made of. Hence, the particle touches on the core nature of the universe and acquires a fundamental position in the standard model, which we use to explain the universe's functioning to us. Furthermore, the discovery of the Higgs boson adds value from a cultural perspective as well. CERN's work on this project is composed of the collective effort of many scientists and engineers that represent a vast set of identities and cultures. It is a true amalgamation of human effort channeled towards a common goal, and its effect on the STEM community continue to be felt today. It is an exciting time to be interested in physics, and I'm glad to be sharing this excitement with so many of you. I would like to remind everybody that you can post all your questions in the chat box on YouTube. We are tracking the questions live, and we will try our best to get to as many questions as possible within today's session. Before we begin our conversation with Dr. Sharma, I would like to invite Ms. Shashi Banerjee, the Director of Education at Shiv Nadar School, to share with us her thoughts on today's events. Thank you.
Thank you, Uday. And Dr. Archana Sharma, isn't it wonderful to have one of our own students in just the decennial year to have us, to lead us into this grand celebration? And I think on behalf of the entire community of learners here, where we have the Vidya Gyan students, we have the Shiv Nadar University, just to say that the voice and the spirit that Vinita Sharad brings into the whole thing, with all of that, I salute the students first, the learners, and Uday, thank you for being there for all of us. And Dr. Sharma, you've been the inspiration. Even before we actually really had you in terms of flesh and blood 4 years ago, we saw you on television when this great discovery was made. And I think we were smitten by the fact that an Indian could do it. And ever since, we have been, kind of exploring so many horizons, so many new things because of this spirit. So I wouldn't take much time except to say that not only does your presence, your work, the visits that our students make, and the entire spirit of research and inquiry and innovation that you have made possible within a curriculum of Indian schools really at large, and that is your life's work where you raised Life Lab Foundation, apart from being the person holding a flag from India at such a prestigious institute. I think I would like to thank you for having Vinita lead us into this great, into this great, I would say, movement of science. And this is not just science, as you say. I can never forget the beautiful composition that we had in person of the Shiva and the Shakti and all of what energy embodies, and the azan from the masjid or the Gregorian chants. I think nothing is really needed to be seen or heard or experienced in isolation. It is this energy. And that is why I think you've called it the God particle, haven't you? So raising more than a toast to the Higgs boson and all that happened ever since. Thank you for also leading the young learners into looking at science in a very different perspective. We have to leave the universe and not the earth a better place than what we found ourselves in. So I think to understand the application of these new findings in day-to-day life is a very important aspect that we would love to hear more from you. And once again, on behalf of the entire Shiv Nadar School fraternity, the principals, we now have a new campus in Chennai, and I wouldn't lose this opportunity to share with you where our new principal, Mrs. Sambasivam, is also here. So is Monica, Anju, and all the other great people here who, on a daily basis, are looking at the adventure of life. And I think the Life Lab Foundation, we thank you once again. So Vinita, this is really over to you and your entire kith and kin and the whole community that you have created. And I'm sure with Dr. Archana Sharma's blessings, with the kind of connects you've made with ITER France, and also I was reading about the Los Alamos National Laboratory and the work. But for us, our real mother, let's say, space is CERN because of Dr. Archana Sharma. So thank you very much. And with that, on behalf, we also have Avnish, the president here, who's the new person who's joined us. Welcome to you, and Padmini and everyone else here, and to Vidya Gyan, to Shiv Nadar University. We hand ourselves over to this session of excitement, adventure, exploration. And in all my excitement, when they called out your name, Dr. Sharma, I just did this, not realizing that people should not mistake me. So we do live in the shadow of your glory all along. Thank you so much. Over to you, Uday, back to you, and lovely to see you.
Lovely to see you too. And I think I'll hand over to Sohana now, who will take us through the session.
Thank you, Shashi ma'am, for your inspirational words. We'll now have a short interview with Dr. Archana Sharma. Recently, there have been a lot of discoveries and inventions in the field of STEM, like the discovery of the God particle, advancement in space exploration and travel, and the groundbreaking research that has been taking in the field of biotechnology and medicine. So, ma'am, according to you, how important is it for the general public to get engaged in understanding the work and the discovery of new things in science and technology?
Thank you so much. First of all, Shashi ma'am, I am overwhelmed by the generous introduction. And I have to say that I feel that I'm back in the fold of the family every time I am interacting with the Shiv Nadar fraternity. Deepest regards to all of you. And I look up to you as educators and inspirational leaders for the new generation. As you rightly said, CERN or any other laboratory is really a means to ignite the sparks in the students and also to leave the world a better place. And that's where we need to really connect. It's not only about the Higgs boson, it's not only about the equations that define the Higgs boson, but it's the impact that it brings to the younger community, how we relate all that to the sustained development goals, and how every student today can connect to solving the bigger challenges we have on the planet. And thank you so much for this invitation. And I'm so glad to be here and so happy to be interacting with the students. And I'm here to answer all questions, of course, whatever I can, because I know that today, if you have access to the internet, www, that was invented at CERN, I won't miss the chance to mention that, you have access to all knowledge in principle. So my role here is just to be here and to be a medium to sort of just nudge you in the direction of where your questions can be answered. Because today's students really, they baffle me with their questions, and they sometimes surpass me in what they can tell us about the subject. So great hats off to the great work that you all are doing in the pedagogy department as well, and in the content department too. So wonderful to work with you all, Vinita ji as well, on the Life Lab Foundation. She's she's really a ball of fire as far as energy is concerned. And I'm really happy to be a part of this session today. So Suhana, coming back to your question, if you allow me, I could perhaps show you something on the screen, if that's okay, a little bit.
Sure, ma'am.
Yeah, actually, I had prepared a small presentation, 10-15 minutes. So maybe we could go through that and pick up the questions as we go. Is that all right?
Sounds good, ma'am.
So I have to share that I was very excited at CERN when I had the opportunity to, what am I sharing? Goodness me. Yes. Am I sharing my screen?
Yes.
Okay. So when we were actually creating the logo for the CERN 10th Higgs boson anniversary, it was a proud moment for me to actually get it translated into Hindi and have India's tiny flag also part of this whole celebration Higgs boson. And indeed, like you said earlier, why should we care about it? That's very, very, and clearly the answers to the curiosity of the students, the teachers, and the world in general is what we are here for. So you know about the Big Bang, that happened 14.8 billion years ago. What we are doing at CERN is creating very large microscopes. So it's an oxymoron that you are creating these very large microscopes, which are called accelerators. And you did see a small film about it earlier. And many of your students have been here and seen this very large magnet, 10 meters, 18 meters long. And we have thousands of them in this 27-kilometer ring around CERN, which is straddling 2 countries. So imagine countries coming to a cooperation level where we are able to have equipments straddling the 2 countries, people working together, in fact, to look at how we can solve the mysteries of the universe, we can impact millions, if not billions of lives, and we can accelerate science in general to to achieve the sustained development goals. And clearly, we are standing on the shoulders of giants. You all very well know that we are, today it seems very obvious, gravity. Everybody lives with gravity, and you can, but it came to the curiosity of Newton. He unlocked the laws of motion time that he actually discovered gravity. And it was mentioned by Uday that when we look at the stars and the galaxies and the astronomy around us, we are able to understand and also predict what is going to happen to the universe in the future. But then this together started as a dream much earlier, which was when Maxwell took all the knowledge of that time and combined, unified electricity and magnetism with equations that many of us study in our schools. And he established the intimate relationship between the electric field and the magnetic field. What does it mean? That we are trying to understand the universe in a way that can help us combine the understanding and perhaps relate what we study in terms of mathematics, physics, astronomy, cosmology into the what we look at nature. How can we not mention Einstein, who has been a role model for us, and the equation E is equal to mc iconic, which helps us to fly satellites, which helps us in our pocket smartphones, and so on. So yes, we are on the shoulders of giants who tell us about how we understand the universe. So elementary building blocks of matter and the forces that control of behavior is what is particle physics. And we study how matter is made of by breaking it down either by microscopes, so we look inside the matter, or inside by the accelerators that tell us on how we can probe matter by smashing protons together. That's where the accelerators come in. So we've understood a little bit about what matter is made of, which are electrons, neutrons, protons that we know, and the quarks that make up the protons too. And the standard model that was also referred to in the early part of our discussion. Now, we know that there are many, many unanswered questions, just like we know that there is something hiding out there, that's dark matter, dark energy. And the dream is to produce this. After making the Higgs boson discovery 10 years ago, 10 years later, we still are unpacking how it looks like. Does it behave as it's supposed to behave? Are there many other Higgs bosons, or are there manifestations of dark matter in our experiments? So huge amount of work is needed. And obviously the students like your students who are very curious and very how can I say, well prepared in this field would be perhaps the generation that is going to be answering these questions in the next 10 years and bringing maybe the Nobel Prize for India. That would be amazing. So yes, there are many, many questions, and we need to look at these answers in these experiments. So how do we do it? We reproduce the conditions of the Big Bang, and that we do by finding protons in this 27 kilometers accelerated CERN, and we go back to the conditions which existed just a couple of minutes after the Big Bang. How do we know that? Because we can study the light that comes out from the universe using telescopes. And that gives us a lot of insight into the structure of the evolution of the universe. So at CERN, we answer these questions. And in doing that, we are privileged to have had people like Carlo Rubbia, Simon van der Meer, who designed the Large Hadron Collider. That was unbelievable that in 1984, Carlo Rubbia got the Large Hadron Collider approved. In 1964, Peter Higgs had actually postulated the Higgs mechanism and how particles could get mass. So from 1964 to 1984, this was the dream that we could experimentally look for the Higgs boson, or a boson that explains the mass of particles and why they are so different. So that's incredible time and effort that went behind creating the theory on the one side and the accelerator on the other side. Simon van der Meer made the special technique called cooling. Cooling means that on the flight, we are able to measure energies, and before these protons can enter the other circumference, of the 27 kilometers, the magnets can be adjusted to the point where we can give a bigger, just by fine-tuning the energies online, and that is called a cold trap or a cold cooling that was discovered and actually invented by Simon van der Meer, for which he got the Nobel Prize. Carlo Rubbia got the Nobel Prize. George Sharpak in the middle also got the Nobel Prize in 1992 for inventing gas detector, which is called the multi-wire proportional chamber. And I have been extremely fortunate of working with him for nearly 5 years when I came to CERN. So this is an incredible journey which came through several decades before we were able to build these machines and to develop technologies, to imagine that these technologies could advance the limits of what was possible. So yes, we built we built the detectors, and my work and my expertise is more in building the detectors. I am a gas detector expert, as Vinita ji mentioned. And of course, we need huge amount of computing. And I think that the number of the years and man years, if you look at, is more than hundreds of man years of thousands of people that has gone into doing this work. So as you see, this is an ingenuity at display, which is the inside of the Large Hadron Collider. And here you see you have a vacuum that is the best vacuum on the planet. You have temperatures that are at which this has to operate, which are created in situ by R&D that went into an energy that is unprecedented on the planet. This experimental apparatus, imagine a 27-kilometer fridge that has to act at close to 0 degrees, absolute zero, for 6 months a year. It is incredible. So before going into too much detail, let's get back to the question that was asked. So I will just stop sharing for a moment, and then we go back to our question. Yes, so Hannah.
So ma'am, the question was, according to you, how important is it for the general public to get engaged in understanding the work and the discovery of new things in science and technology?
Okay, so let us imagine the big challenges we are facing today, the Earth is facing as well. Let's look at the environment. For example, let's look at climate change, and let's look at imaging what's going on in the world. So suppose there are natural disasters, we need to do automatic relief. For this relief, we will need to have evidence-based decision making, right? What does it mean? We need to take pictures from the sky, from the satellite. We need to know where the disaster is, and we will be able to give a response, an emergency response. For that, similar technologies, like we look at the collisions, similar technologies of imaging are used by satellites, and data analysis for these images, just like we use in the collisions. So we are saving lives, we are saving money, and doing humanitarian work just by using very similar algorithms that have been developed together with an agency called UNOSAT. UNOSAT is the satellite, the agency is called UNITAR. And in over 15 years, this work has been developed. There are many examples, I could go further. but maybe we have other questions too.
Thank you, ma'am. That was really enlightening for all of our viewers. Viewers, please note if you have any questions relevant to the question asked, please write it in the chat in the meeting or on YouTube. Now over to Praneel.
Thank you, Suhana. The discovery of the Higgs boson is considered one of the 10 greatest discoveries of all time in the field of STEM. Having said that, we students really want to know, how do scientists collaborate, work, and think in order to make groundbreaking discoveries?
That's a wonderful question, because I really have to bring you back to sharing my slides, first of all, so that you will see what I would like to say here. And so here am I near my experiment, right? And this is a piece of equipment that has been installed in the shutdown, which you saw in the film that was shown before. And this is one of the last detectors being installed before the experiment was closed. So the question is about collaboration and about how people work together, right? Let me just get there. So you can see not alone. We need a huge collaboration on the planet to come together, simply because we need expertise in many, many different fields. As you saw earlier, you need the physicists who are really creating the physics case, which means we are looking for the Higgs boson. And why are we spending, billions of dollars in looking for the Higgs boson? That isn't it? So we need to understand how we come together, and we are able to fit pieces of this huge apparatus together to look for the Higgs boson, which is like a needle in millions of haystacks, if I can say so. That's where we have the power of collaboration. Each group or each university or even school children have been participating in building the experiments. This can be broken up into tiny pieces, and I know that for sure that some part of the electronics boards were tested in several schools in the United States. So those are the dreams to have, where even in India, school children can participate in in contributing to either designing or testing or building or quality certifying in part of these experiments of the future. So yes, collaboration is unbelievable because the challenge is incredible. So imagine to be at the same question for decades, to build a machine that doesn't exist. We did not know how to do it. So we have to first look at all the theory, the prototyping, working history. What you're looking at, the experiment on the top left and also on my background, the weight of this experiment is 14,500 tons, and it takes data in 100 million channels, where at the rate of 40 million times per second. So that's the kind of data we are looking at. We are looking at 200 or 250 petabytes of data per year. So how do we do it? One person alone or one group alone cannot do it. Even one country alone cannot do it. So we need to come together. And despite all these difficulties, we found it. And here you see Fabiola Gianotti, who is now the Director General of CERN, and some of our directors on the left, and the signal of the Higgs boson, the first signal that announced in 2012 on the 4th of July. That's why we are celebrating the 10th anniversary, right? And on the right, you see the spokesperson, Joe Incandela, who is the spokesperson of CMS, who, that's my experiment, by the way, also reported on spotting, I would say, the Higgs boson in CMS, which is why the Nobel Prize was then given to Peter Higgs, Engelbart, and Francois Engler, sorry, and that Nobel Prize was based on what was found at CERN on the 10th, 4th of July in 2012. So let's move to another question, Praneel.
Thank you, ma'am. That was really nice to know. So we have a few questions from our viewers. Firstly, we have a question from Siddhant Singhania. What are CERN's major goals for the third physics run of the Large Hadron Collider?
Okay, so the major goals indeed are to study the Higgs boson. It's like, you found it, you've got 10 years of data as well, of which you have, the 3 years of shutdown as well. So within 2 years of restarting the LHC in 2010, we found the Higgs boson, but it was just a finding, a discovery. Now you need to study it. It was established that it's a Higgs boson because it behaved like one. It was a spin zero particle. However, we need to understand further the decay modes, other Higgses that could be produced. Is there going to be another discovery? For example, could we spot dark matter? So these are the kind of questions that we are looking at.
All right. We have another question. Why is the Higgs boson so difficult to find?
Okay, so the Higgs boson itself is relatively produced at high energies, although it's a light boson, 125 GeV. But imagine that you have to make an elephant out of a dough, Play-Doh. You play like plasticine, you play, but you do not have enough plasticine to make this large elephant, right? So the energies that were there in the previous collider, that was the LEP, we were unable to produce. That did go up to 200 GeV, but we were not able to produce the Higgs boson in the previous experiment, in the previous collider, LEP collider. Then in the proton-proton collider, the energies went up and we could produce the Higgs boson, because you need large amount of energy to produce the Higgs boson, right? In addition, it is very rare, because if it was very, very frequent, you would just produce it every time you have a collision. But the probability is like 1 in 10 to the 14. So imagine that how much data do you need before you can spot one Higgs boson. So you need to have, to claim a discovery, you need to have a 6 sigma, in the sense that, you have measured, you've got so much data where you can say for sure that this is my discovery. So, and then it is an unknown particle, so we do not know how it would behave, right? So we needed to have a lot of work done in terms of looking at the signatures that we would see in the experiments. So all those studies were done. Signatures were defined that it would decay into 2 photons back to back, and it would decay into leptons. That was also foreseen. And then it did exactly what it was expected when it was discovered. Okay.
Absolutely, ma'am. So we have a question from Urjit Mahajan. So, ma'am, could you please elaborate more on the applications of CERN's research for other fields like medical imaging and diagnostics?
Okay. So I'll share my screen again, if you permit me, because it will show you something nicely.
Sure, ma'am.
Yeah, let's see. So yes, we have many, many, many important applications in medicine and healthcare. So first of all, imagine the cancer burden in the world. Particularly in India, we have 1.7 million new cases of cancer per year. And at this moment of time, we desperately need these kind of technologies in our country. So young students, this is a field which is a very growing field. In the world, in the last 4 years, we have gone from 25 facilities to 106 facilities. And accelerator technologies should be used for treating tumors. Why? Because when you treat a patient with radiation, you must have heard about, of course, radiation treatment for cancer tumors. you are shining the radiation on the full body. So healthy tissues also are damaged as a collateral damage to the treatment of the tumor. And that debilitates the patient's quality of life and also the life expectancy. Protons or other particles, we can tune the energy in such a way that only the tumor be damaged. So you paint the tumor with the proton energy, and that has turned out to be amazing revolution. It is very much already in practice in the West meaning Europe, United States, and Japan. So, of course, the dream would be to create a facility like this in India. I'm making it very India specific, and this is one of the applications. Technologies are used in imaging, which I hinted to earlier, not only for disaster management, but also for imaging where the tumor is. Inside the body, we can do X-rays, but again, X-rays give a lot of dose to the body, but we can use now advanced energies for imaging inside the body in situ, because the body is a moving object, right? The patient is also breathing. So we are able to do outstanding fine resolution 3D color imaging so that doctors can do non-invasive studies of the inside of the body. And that's, of course, and CERN is producing a lot of spin-off for nuclear medicine and research as well. So I think you can see here, sorry. Does it answer your question? That's a small video that shows you on how medical, you can see this is what the doctor will see instead, and you can compare it to what the doctor would see in a black and white X-ray, which is the norm at the moment. Okay.
Yes, ma'am. Thank you, ma'am. That was really nice to know. It's good to know that CERN's technical innovations even have an application in medical sciences. So now over to Suhana for the next question.
Thank you, Pranil. Ma'am, I've always been curious to know, why has the Higgs boson been named the God particle?
Okay, this is a funny story because there are two reasons which I have heard from, corridor conversations. So the first is, of course, like Shashi ma'am said, the God particle gives mass to the universe. And from where does that come? To understand something in science, you assign it to God. God has done this. All right, great. However, as scientists, we need corroboration of whatever we say. Science must be explaining nature. So personally, I don't buy that argument, but let's go to the other argument. Why is it called the God particle? So Leon Lederman, who was the director of Fermilab, it's another organization in the United States like CERN, lower energy, we have the highest energy. And he wrote a book on particle physics and the Higgs boson because they were quite disappointed that they could not find the Higgs boson at Fermilab. That's clear because they had found the top quark. So on that book, he wrote on the cover, the goddamn particle. And the editor did not like it. The editor said, this is not a good cover. So he took away the damn part from there and it remained the God particle. And that's how it was called the God particle. And it caught up in the media. Everybody likes to call it. And it's fun as well. And it's God's energy. So we can revel in the fact that we can connect this also to Shiva's cosmic energy. So yeah. Does it explain your question?
Yes, ma'am, very well. We've received a question from our viewers on YouTube. How much energy does the collider use? This question is from Divyam and he's joined us on YouTube.
So how much energy? You mean power?
Yes, ma'am.
Yes, of course. The power we have is huge. It's like a township of 15,000 people, of a city, and we are actively working very, very hard on how to reduce this energy footprint. and make it very green as well. So most of the energy of CERN comes from France. And you know that France has 70 to 80% nuclear energy. So we are in principle green. However, we can do much better. So the energy really, you can equate it to that of a small town when the accelerator is working.
Thank you, ma'am. I think it answers our questions very well. Now over to Pranil.
Thank you, Suhana. So, ma'am, as you know, we are all here to celebrate 10 years since the discovery of the Higgs boson in July 2012. Therefore, we would like to know what exactly is the Higgs boson and what contribution has it had to the field of particle physics?
Okay, so the standard model, as you may have learned or will learn, is really in very lay terms, just like the periodic table of chemistry. We are able to put all the particles that have been discovered over the last century from the 60s and 70s into a model, which is called the standard model of particle physics. In this standard model, you have fermions and bosons, and you have force carriers. The force carriers are the photons. So you have the electromagnetic force, you have the weak force, the strong force, and the gravity, right? So photons, bosons like W and Z bosons, they represent the force carriers for the weak particles. And the Higgs boson was postulated and nicely consolidated in the 60s and the 70s on a mechanism by which particles can have mass. Because it's a strange question. Why are particle masses so different? Why is a proton so heavy? Why is the electron so light, right? So given the Higgs mechanism on the one big, let's say, equation that was formulated by Francois Englert, Braut, Kibble, Higgs, they explained that in a field of the Higgs, when any particle interacts, so the amount of interaction is what will give it its mass. So just imagine that, you all, the young students, of course, are in a big stadium, okay? Imagine that. And in this big stadium, we are waiting for a rock star to arrive. So who could be a good big rock star today? Tell me, Pranil.
Well, ma'am, you can choose.
No, I can choose. I don't know the new rock stars, so that's why I'm asking you. Can we think of Amitabh Bachchan? Say he is not a rock star,
Sure.
but that's whom I know. Okay, so imagine that he is coming, and I think he is liked by generations, so it's okay. So suppose he is entering from one stadium, and this packed stadium comes to know that he has entered. Something will happen inside, isn't it? People will start talking to each other, and some people would want to go and meet him or take his autograph, right? So without knowing, without actually doing anything, just by the knowledge that this star is here, something happened to people, right? Similarly, in the birth of the universe, when particles did not have mass, and they acquired mass because of the Higgs mechanism, that when the Higgs, the star particle, the Higgs boson moved around, and in this Higgs field, particles interacted with that field, they acquired mass. So depending on how far you are from the star, that's the amount of interaction you had and how much you wanted to have as well, depending on your character, right? So that's why it's extremely important to understand how we are able to give mass to particles. And once we have the Higgs boson discovered, that really completes the puzzle of the standard model. That was the only missing piece. Everything else was in its place, the families and the leptons, everything was in place. But the Higgs boson was not discovered.
Okay, ma'am, that gave us a really detailed explanation and insight into the structure of the Higgs boson. So, but ma'am, there's this perception that the Higgs boson gives mass to other particles. But how is it possible that a particle gives mass to another particle? So, like, could you please elaborate on this?
Look, so these are the things that we are going to look for in the next runs on how Higgs interacts with itself. Where did the mass of the Higgs come from? The chicken came first or the egg, in simple terms. So there's going to be a lot of debate, and you are the young students who are going to pick up the baton and take this forward. So imagine Higgs self-coupling. How does it work? Because this is such a strong field, and there's another Higgs, or in which way does Higgs interact with the vacuum? And I'm not going to say anything more, because first of all, it's not my subject directly. I work on creating the detectors which measure the Higgs boson, So the point I'm trying to make is that it is a complicated matter, and we need to make more studies, which is why we need to run the accelerator for another 10, 15 years. By the way, until 2037, it's already agreed that we are going to run. So there is another career in front of us.
Okay, ma'am, so you spoke about the Higgs field in the previous question. So, like, does this Higgs field generate the mass of every single particle or only selected?
No, this is then the mechanism is for the particles that are in the field, in space, right? So if you look at the time just after the Big Bang, immediately after the Big Bang, there were particles without any masses, and there was the Higgs boson, which, because of its mechanism, got these particles to acquire masses, right? So it's every particle that feels the Higgs force. Does it
Okay,
answer?
ma'am. Yes, ma'am, sure is.
Okay.
So, thank you. That was really amazing. Like, I get great to know such new stuff. So now over to Suhana for the next question.
Thank you, Pranil. I wanted to ask a question from ma'am that often comes to my mind. There are very few women in the field of STEM. Are there greater challenges faced by women in this field?
Okay, before going to that question, Suhana, can I answer? I see a comment from Shashi ma'am on curious about antimatter. So Shashi ma'am, if I allow myself to shake hands with you virtually, and you are made out of antimatter and I am made out of matter, what's going to happen? If we shake hands, both of us should disappear into energy, correct? However, we don't, it means both of us are made out of matter, correct? So if we take the same argument back in time to when the Big Bang happened and the world was created, then the world should not have been created, because matter and antimatter should have been made in equal proportions. But this didn't happen. There was an excess of matter, and that's why we are here. Now, why is this excess? That's a question we want to understand, and we are going to study in the next runs also. There is an experiment dedicated to antimatter studies, and that's called the LHCb experiment at CERN. I hope that answers your question.
Thank you. Thank you so much. And as somebody, I think Shilpa was saying, or someone, that it's so easily made understood. I think it's a lot for us teachers to learn. Thank you so much for your analogies.
Thank you. And now coming to the woman part. First of all, I'm so delighted to see so many women educators. So that's fantastic. And of course, that doesn't mean that men are any less, So I know the women are good and they take the baton forward. However, it's not all rosy, as you rightly say. It's challenging, and particularly in my time, it has been very challenging. Perceptions have changed now. People are expecting excellence now from girls too, and that has changed a bit the scenario so that girls can also be outstanding, you see, because when you do not expect that girls can be equal, if not better, that really diminishes a person's morale and psychology on how they can go forward. So these are stereotypes, they exist, they are within us, and even when I came to CERN in the 80s, I was told so many things. I am, people would assume that I am not anything against secretaries, with all due respect, that I am a translator or secretary in the United Nations. They would assume that, because first of all, Indians were not here at that time, so many not there. So what is this woman doing from India over here, first of all, and second, a scientist, oh my God, how can you be a scientist, so that's also quite a challenging thing that I had to, the mental picture of a woman scientist was not common. But that's why, I am really pushing on reversing this. And I think in our country, particularly in the metros, people are expecting excellence from girls. And we're not talking about our journey at the moment, about my journey, but in general, I think now the field is quite level, and particularly for young students like you, I think nothing to stop you to go as far as you can dream. So you absolutely need to dream, and that's where you should not stop. I want to just share another thing, if I can. So there is this book which is called Nobel Dreams of India, the first one. It is available for free on this link. Neeta ma'am can circulate this. There's another book called India's Science Geniuses. It is very audacious, but it brings a lot of women scientists here. And there is a book called The A to Z of CERN, that is also written by two young students who could not come to CERN during the pandemic, and we did this work together. So I will encourage you to get, I don't think that you lack motivation or role models in your environment, but do take a look to these three books, and it will be interesting to see how women, despite having to bear children, that is something that you can't change. You have to rear the children as well, you have to take care of the children as well, but I want to add dare as well. You will go as far as you will dare. So that's what I would like to say. Thank you.
Thank you, ma'am. I think that is very inspirational for all of our viewers, and especially girl children who are watching us today. We've received a question in the chat box. How is the data received from space satellites and telescopes used to study the behavior of light and do experiments at CERN?
Behavior of light?
Behavior of light.
The data from satellites? I didn't understand the question, I'm sorry. So from satellites, what we are doing is really that with UNOSAT, as I explained to you also, from UNOSAT, let me see if I have a slide on that, then it will be easier to explain. So on the satellite part, I'm not sure if I have a slide today on that. No. So yes, let me just say that imaging satellites are based on sensors, and there are many sensors, number of sensors that we make at CERN for measuring radiation, for measuring movement, for doing alignment. This experiment behind me, this is very, very large and heavy experiment, but we are measuring very tiny things, right? We are measuring things that, first of all, exist for less than 10 to the minus 20 seconds. And they leave traces in this experiment, which are smaller than, few microns, few tens of microns, or hundreds of microns. So how do you do that? For that, we need alignment of these very large objects, because if they themselves move, how can you measure something finer than the misalignment? So techniques, algorithms, computing advancements, for example, quantum computing, artificial intelligence, and neural networks and machine learning techniques, they all have been very much advanced using our data, which can then be translated into using satellite data, financial data. Stock markets are using our algorithms as well. And so many physicists go to the finance sector. And the reason is because they know how to deal with data. So I hope partly I can answer that question because I didn't understand the whole thing. Yeah.
Thank you, ma'am. I think Vinita ma'am has something to say.
Thank you, Suhana. I just want to assure the viewers on YouTube, Dr. Archana, there are many questions and you will be thrilled to see these questions from young minds. Viewers, please note, this is not the first and last session. This is just the first session. On behalf of Life Lab Foundation and Shiv Nadar School, we promise that there will be a series of webinars. This is the first one. We will be addressing all these questions. And obviously in the month of August, the next session will be there, right, Dr. Archana? So because the type of question asked by this young minds, believe me, Dr. Archana, I have a goosebump. And I'm so happy that you can make this possible when we approached you. Thank you very much, viewers. Next session will be in first week of August, and moderated students will be from Shiv Nadar School, Gurgaon, and Vidya Gyan and University. Over to you, Uday.
All right, thank you so much. I'm not okay. Yeah, okay, I can see myself now. Thank you so much, Dr. Sharma. I mean, I've been studying physics here for a while, but like attending this session was really fun, even though it's not like the area of physics that I'm studying, but learning about what CERN is up to is always refreshing, and I'm waiting for the day I can be there physically for sure. And as always, your thoughts and insights shone light on some essential questions that I'm sure pervade the minds of all the young scientific minds in our audience. And I think they will be happy to know that this is only the beginning of our pursuit of the God particle. As Vinita ma'am pointed out, we will continue to engage with the topic by delving deeper into the realm of particle physics. Today, we only touched on the core idea of Higgs boson and what makes it so important. But as we go on, we will be discussing these concepts in more depth. So if you found today's conversation interesting at any measure, be sure to stay tuned for more, because I know that I'll be coming back as an audience member for any future sessions. Thank you so much for devoting your time to science today, and we look forward to seeing you again. In future sessions, we will be looking at concepts like antimatter, which is something we discussed very briefly today. Do parallel universes exist? What's the Fermi paradox? And stuff like that. Just fun questions in science that are always very refreshing to discuss. Now, before we close off for tonight, once again, thank you, Dr. Sharma, for giving us your time. And may I request Ms. Monica Sagar, the principal of Shiv Nadar School, Gurgaon, to share her views about the session and deliver a vote of thanks, please.
Thank you, Uday. Thank you, Dr. Archana. It's been, what can I say? I'm looking for words, for good adjectives, because they fall short of what we just experienced. You know, the way you handled all the questions, likening the boson particle to an Amitabh Bachchan, and making it so human. In fact, I think you simplified everything, and you showed how a good teacher, all she needs to, or all he needs to do, is simplify complex things. We don't understand too much about space at the school level, yes, but you're making it so much more understandable. Thank you so much for giving your time. Thank you, Pranil, Uday, and Suhana. You know, for really bringing out the best questions to the fore. and getting us this time with Dr. Archana. I remember reading somewhere that Albert Einstein had said it's a miracle that curiosity survives formal education. He said it many years back because he himself, I think he was not too happy with his own schooling. But I'm happy to say that the schooling at Shiv Nadar School has brought that curiosity to the fore. And Vinita ma'am, you with your dogged determination to make sure that all children, find that love and the curiosity in the physical, chemical, biological world around us, that you make sure they don't sit idle and they are forever curious. Thank you so much, Shashi ma'am, Avnish, Samir, Anjusoni ma'am, and everybody else who are here from the Shiv Nadar Foundation family, I would say, members from Vidya Gyan, members from the university, from across our campuses. It's been a wonderful start to the power of 10. And Dr. Archana, while it is the 10th year of discovering the particle, it's also our school's 10th year. So that's why we met, I suppose. There's some similarity there. And you brought out how important it is. Thank you so much for guiding our teams of staff and students on this curious journey. I think Colonel Gopal keeps saying that wonder and wander are the two beautiful things or habits that all children and staff need to have, which are the basis for lifelong learning. And so this is an additional, I think, addition to the repertoire of what the children can be exposed to. Thank you so very, very much.
My pleasure and privilege to be here. Sorry, I'm interrupting the flow, but it's really, really a privilege for me to be here. And I really look forward to interacting more and perhaps one of these days personally as well when I come to India. So also to Uday, I think it's late night over there, right? It's early morning here. So we can, time zone don't matter. Yeah, time zones don't matter. We will keep the spirit and keep going. Thank you. Thank you for your kind invitation and the generous appreciation. Thank you. We'll continue to do that. All the best. Bye-bye. Thank you.
Live streaming.
Thank you.
Live streaming.
Thank you.